All right, I think it's time to start. Just make sure that you can hear me. I want to ask again, can you hear me now?
Yeah, yes. I can still hear you.
Okay, thank you, thank you. A couple of comments that I wanted to make before we start. So I will give you this weekend another survey just to see what kind of changes. Now this is at the end of 4th week, so practically we are almost done with a quarter, if not a little over, of the semester. And I wanted to make sure that if there is anything that I can do from my end that is practically doable and logical, that I will do the best I can to help. I also understand, that online is a challenge for everybody, including me, the professors, the faculty, and especially for the students, considering that many of you may have access, may not have access, may have or easy access, may have other problems and so forth. Having said all of this, I also wanted to say that this is not an easy class. And as much as I try to provide you with information, the most information that I can, everything that we do in class, it's on video, all of the lectures are there ahead of time, all of my notes, then they are uploaded afterwards if there is anything additional, and the problem solving sessions and the whole thing. And in fact, I will also put the solutions for last week and this week on the homepage. So if anything, I'm afraid that there is overwhelming information that I make available. However, I wanted to say, I have seen that online participation in class is not at the level that I would like to see it. A lot of students think that they can view the video and as soon as they can make it available, it's the next day or definitely before the class, the following lecture. And they think that they can pass the class without necessarily participating actively. And I have to say, this is probably not going to happen. I have taught this class multiple times. This is the first time, and I have used Top Hat. This is my 4th year in a row, not 2 years, twice in this university and twice in my previous institution. And this is the first time that I see, I have not changed the questions. This is the first time that I see so poor participation and also accuracy. And I have come to believe from also some indications that people do not come to the lecture. They don't come online while I'm teaching to get the information. If I give you anything, if I tell you something about the exercises, and they try to do it on their own, and of course they fail. Now, getting the 15% for participation and failing consistently in the answers, it says one thing. It says that the participation has been there, but your learning has not been there. And I worry a little bit about that because it's not just merely about passing this class. This is not my goal. I would like you to pass and learn. And so I just want to say that I worry about what I see. And after I get your survey, I will also spend one lecture to go over the survey and also tell you my observations so you can hear my feedback as well, because I think it's important for us to provide feedback both ways. But I just wanted to tell you that please connect to the lecture. You cannot learn without being online. If you think that this is an online class that you can take an online degree, it has not been designed that way. For an online asynchronous degree, there are other tools that people use for learning, which we do not have available right now. So this class is online because of COVID. Has not been designed to be an effective class for asynchronous online delivery. I just want to say that. So if you think that you can learn without interacting with me, then I don't believe that's going to be true. And I see also from the questions I receive in class, for some students, familiarize yourself with homepage. I don't know how else to make the information. I have put everything on the homepage, so you don't have to wander inside Canvas. But please make yourselves familiar. Connect with your teams, and make sure that you know the other people. I even realized that as of yesterday, as Wednesday, there were people who did not know what their teams were. I mean, I understand I finalized the teams on, I had them in place for a long time. I finalized them this past weekend because of changes, and I believe we are 99% there. But please find your colleagues and start working with them. So that is some comments I wanted to make. And also, I wanted to make, before I start, some comments about your homework. And also I will have office hours on Sunday, about homework. A lot of, some students, not a lot of students, some students asked that the team homework was a bit confusing. I just want to tell you, I will make comments about the homework as I'm solving this problem. This problem that we have in front of us, it has a charge sphere. Before that, we looked at charges that were distributed either on, it was a point charge. There were charges on a line. There were charges on a surface, like this one that we saw last time, and distributed on the surface. So we start. Oh, sorry. Okay. Thank you. Share. Okay, so this is, you will see, this is what we started with last time. And I said that we started with a point charge. We went to a line charge, infinite and finite. Now here, last time we went to a surface charge. All right, so we go one step at a time from a point to a volume charge. And today, we are going to go to a volume charge. In all of these cases, starting from the point charge to this volume charge, to find the total flux, we have to integrate on a volume all around the charge itself. First of all, this is the first thing we do. And then we decide probably to integrate another, it depends on the problem. So for your homework, in your homework, you have the following. In the homework, you have a charge, a point charge, and it is at the edge, at the point, that point of a cube, like this. And they are asking you to find how much of the flux, of the total flux practically, so this is the flux density, all right, the electric flux density. The total flux of this charge Q, it will be the volume integral, excuse me, of The total flux of this charge is gonna, well, let me start with the divergence theorem. This is your flux density. The divergence theorem says that the divergence of dV equals the surface integral on all of the surfaces. So let's assume now, forget for a moment, and I will erase it. Forget about this for a moment. That was the homework. Now we have a point charge. What we did with a point charge, we took a volume that includes the charge. All right, so we took this volume. And then we applied the divergence theorem on D, which says this one. If D is the flux density, the electric flux density, and S is the surface that encloses this volume V, then this one here shows the total flux of that is created by the charge. And if you remember, this charge is going to send an electric field in all directions, all right, like this. So by taking this, practically this here, you find the total flux. Now, your volume can be anything, any shape. Usually we take a sphere for a point charge, but it could be any shape. For example, your volume could look like a cube. And the center of the cube, you could have your charge. All right. And so here could be the charge at the center of the cube. The question then, instead of, now, if you were to solve the same problem, and if you knew the total flux, which is here, then practically, if your charge was at the center of a cube, you could, of a cube, all right, not a cube that has equal sides everywhere, then practically you could tell us how much was the flux that would go through one surface. Okay, so keep that in mind. Now, the homework that I gave you places the charge at this tip point of a cube. So the cube is this one. And knowing everything that I told you is asking you now to find how much flux in this case, what portion of the total flux will go through this surface. So to solve this problem, you will have to solve this problem. Let me draw this a little better. Okay, let me draw this, remove that. You remember what I told you for this one? You have a cube. And then your charge here is at the center of the cube. Okay, let me also erase that to put it at the center. Here. Okay, you know this here. And then you can find how much flux goes from out of each of these equal surfaces, which are squares. You have from here to go to this one and find this, the flux from here, and then from here to go and solve this one. This is how I would solve that problem. Okay, so think it's more conceptual. There is nothing, I don't want you to do any equations, nothing. It's a conceptual problem, and I want you to describe it. So that's what I would like to give you as a hint. Any questions? Okay.
I just wanted
Well,
to
yes, go ahead. Go ahead.
at least on the picture that you had before, when you had the charge in the center of the cube, um,
Mm-hmm.
going like, and you pointed out like the top surface, you were just saying like in that example, we were that when you compared it to the point charge that had like when we're dealing still with 2D space, and it was just like a surface, it's like the same thing. Where if we're dealing with that top surface, you're dealing with like a surface that's just like that circle surface. It's
Yes,
the thing, right?
yes, but so you have to remember something. Yes, you are absolutely correct in what you're saying. But I also want to remind you the following. When you have a charge Q, the total flux, which is this one, is independent of this type of surface you're creating around the charge. So your total flux is going to be the same whether the surface is a sphere, the surface is like this, or the surface is a cube. Is that this is key to solving the problem. Is that clear?
Yes, but then I'll ask this question as a follow up. Um, when you're saying that the total flux will be the same regardless of like the surface, will that mean that it would be the same? Like, let's say we're dealing now with the 3D space, that it would then be distribute that like would that mean that like total flux, for example, if you're dealing with a cube, is like every surface is a sixth of it due to the fact that, like it'd be spread out, or is it just like it's a surface, it's the same thing. So flux here is the same as flux here, is the same as flux here because it's all just one surface.
So you have to remember, start number one. The flux for a point charge distributes in space. I mean, the lines, the field lines from a point charge distribute evenly. All
Yeah.
right, evenly. And then the total flux, how much is the total flux from a charge Q? How much is this one actually?
Uh, Wait, you're saying how far is it? Oh, or how much is it?
How much it is Q. You always need to remember that, all right? Regardless of the volume, regardless of the size of the shape and size of surface, the total flux is independent of the volume and independent of the surface, the shape of the surface, right? Or the size of the surface. I can
Okay.
put a sphere that is very, very close to Q, so it's going to be a teeny sphere, or I can put a huge sphere that can be at infinity. Still, the flux is going to be this.
Gotcha. Total flux.
Right? That's the key.
Okay. All right. Thank you.
And then how much is going to come out of each surface depends on how now the total is going to be the same. But how much is going to come out of each surface, say, of a cube, depends on how you space the cube in relation to the charge. Now, maybe from one surface to another may change or not, depends on how the charge is situated, but the total flux is going to be identical and independent.
Okay.
All right. So if you keep this in mind and go the way I told you, from here, from 2 to 3, then you're going to find the answer. Any other questions on this? This is a problem. It's conceptual because you have to think it through. Don't write equations other than this one. Well, this is fundamental, which I wrote you right here. But nothing else you need to write. Think it through. That's why I like these problems, because you don't get lost into math. Because sometimes if math is extensive, we get lost into it and we lose the sight of the physics. So this one is just, that's why it is important to work with a team, because you can talk about it. All right, it helps you. The conversation will help you come to the accurate result. Any other questions on this? More questions, you can come on Sunday. You know, if still until Sunday there are some issues, let's talk about those then. Okay. All right, hearing none as comments, I will continue then and start with this one here. So I will take this. All right, so now we want to see, we start here with a field from a volume chart. And what I wanted to say in all of this, you remember, in all of this, first of all, we want to understand in problems like this, what kind of a charge we have. Is it a point charge? Is it a line charge? Before you even try to solve anything, you have to read the problems carefully or the statement of the problem, and then understand and then think exactly how your charge is distributing. Try to think it through, all right? Sometimes that's why we do shapes here, because visualizing it is important part of solving the problem. So visualize how the charge is. In this particular case, your charge distributes evenly within a volume that has the shape of a sphere. All right, so it's evenly distributed. And it's called volume charge because obviously we give the charge density. It's a volume charge density. It's measured in coulombs per unit volume, in this case, meters cubed, for example, and distributes evenly through this sphere. And then we give the size of the sphere by its radius. One interesting thing, first of all, in three-dimensional problems, what we are looking for are symmetries. Remember, we said that before. In this particular case, our problem has a spherical symmetry. What does this really mean? That the 2 points located in different places, one here and the other there, say A and B, which, however, have the same distance from the charge. All right, if they have the same distance from the charge, let me do this more accurately. And this is, so OA equals OB. Then these 2 points feel exactly the same electric field. And that is called spherical symmetry. The problem is spherically symmetric because the source, the electric source, which is the charge, is spherically symmetric. And the whole problem then, which is just a sphere, and it has a uniform charge density, is going to create a field that also is going to have spherical symmetry. That is important to remember. Okay. Now, so I write it here. So spherically symmetric. What then? How do we find, in this particular case, we need to find the field. And they say, in this problem, they say, find the field everywhere, inside the sphere and outside of the sphere. So we start with the field inside the sphere. Excuse me, outside of the sphere in this particular one. Okay, so what do? We go and we specify a volume, and the volume is specified by this one here, by this spherical surface. And we call V the volume within, all right, that surface. This surface is S, and you see the direction of the surface, which is perpendicular to the surface, the direction of the surface is perpendicular to the surface of the sphere and is pointing outwards. Remember that, all right? So if you have a volume, the surface that encloses the volume has a direction. Obviously, all surfaces do have a direction, and the direction of the surface is perpendicular to the surface and points outwards. So this one, the direction of this surface is here. It shows here. All right. Now, what do? We start with Gauss's law. And Gauss's law says that the divergence at any point in space, and in fact here, since I will add a page so I can, so Gauss's law, so as a note here to remember. So Gauss's law, what does it say? It says that if I have a charge distribution or anything, if I have charges here, it could be a uniform distribution, it could be point charges, all right, it could be anything. So if this is a collection of charges or it's a distribution, so I will call that Q. And Q obviously, whether it's a collection of charges or whether it's a okay, whether it's a collection of charges, could be smaller ones if it's a collection, or it's a distribution, or that represents a distribution. All right, that is going to be a function of space. So obviously, since I am in 3D, I will indicate that by R, and in fact, to be accurate, it's going to be R, theta, and phi. And since I have both theta and phi, I don't need to put the R as a direction. So, you know, let me in fact also remind you, either, this is too big, either you're going to say that, or you're going to indicate Q as a function of R. Why is that? R, theta, and phi are three coordinates that just show how R is defined, the direction of any point in space. So if I have a point of reference here, so you remember, if I have a point of reference, this is a point of reference. It could be the center of a coordinate system, but as I call it, point of reference. All right, this is O. If I have a point of reference, then any place where I am as an observant, and let's assume that this is my place as an observant is here, P. R with a bar is this one. Okay, now this is always accurate. If you say that at point P or point P is given from a point of reference is defined by R, so you say that my point P, you can sometimes write it like this, then practically having the point of reference O defines the position of point P accurately, all right? If you then decide to center around point O a spherical coordinate system, then R is equivalent to saying R, theta, and phi in spherical coordinates. And in that case, these two are equivalent in terms of defining a position. So just to remember, to remind you also. Now, Gauss's law says the following. that at any point in my space, at any point, where in this space that has charges, okay, D, which is the electric flux density, has a divergence which is equal to the value of Q at that point in space. This is Gauss's law, very important. What does that really say? That says that if my point in space happens to be at the place where there is a charge, that the divergence of the electric flux density is equal to the charge at that point in space. If at the point in space where I am, there is no charge, then what happens to the divergence of D is equal to what if there is no charge?
To 0?
0. No charge. This is Gauss's law. Okay, and as I said in class before, I always start with Gauss's law to develop accurate expressions for the field because it's the easiest one to start with. An equivalent to Gauss's law would have been Coulomb's law. And Coulomb's law would say that the electric field everywhere, or the divergence, if you like to go into the electric field or the electric flux density D, all right, in fact, where D is equal to E divided by epsilon naught, either one would be equal to 1 over, let me see, in fact, I will, let me do this, wait a second. Let me write this that you have. And I wrote it differently, in fact, because what I wrote was not correct. And that would be D over epsilon naught. All right, that is the correct one. So E is going to be 4 pi epsilon naught. Okay, am I right for this? Yes. Q over R squared, and will be along the direction of R. Or you can see it as 1 over 4 pi epsilon naught. And it will be Q of R, or I said will be like this, cube. And why is that? Because A sub R equals R. Okay, where alpha or A sub R is the unit vector. This is a note, so you can remember that this is what we have in mind, in the back of our mind, when we write Gauss's law. And why do I start with Gauss's law, which is this one, the one in the box, and not with Coulomb's law? And this is Coulomb's. Because Gauss's law is a lot simpler, this one, than Coulomb's law, which is this one. All right. So personally, you can do either one, and then you will come to the same outcome, but it's always easier to start with Gauss's law. So having said that, we go here and we take the divergence theorem, all right, for Gauss's law, which says that the volume integral of the divergence of D equals the closed surface integral on a surface of this volume. And here, because we integrate, and of course, this is going to be the closed surface integral. So you practically, this is going to be impacted. The closed surface integral is going to be the closed volume integral of Q, which is the volume density. I have not included this intermediate step. It was going to be this Q, which is a function of position, obviously, dV. All right. And that, because the volume includes all the charge, this volume integral for the charge density is nothing else but the total charge Q, number one. Number two, because this is spherically symmetric and the volume that I have considered around the charge is a sphere, and the surface where the surface integral happens is the surface of the sphere. And because it's spherically symmetric, all the values of the D vector on this surface are equal because they are the same distance from the center of the spherical system. And therefore, the closed surface integral gives us this. All right. It's, of course, the dot product between the electric flux density D and the normal vector N, which in fact, as a result, gives us what? This component of D, which is the radial component of D. So it tells us at the end that the field that is radiated, that is excited by this spherical charge, which is uniform, is a field that has only the radial component, like here. And this radial component is given by that. So what is interesting in all of this, and that's what I want you to remember, is that when you have a volume charge that is enclosed somewhere, and you are totally outside of that volume, and you have you sense a field that applies, then this field, no matter where you are, is going to be as if the charge was all concentrated in the beginning of the coordinate system. Okay. Now, something else that I would like to bring to your attention here, because that is important to remember. Let me ask you the following question. Let me just make this smaller. Let me ask you the following question. Let's assume, it is not so here. Okay, here. Let's assume, I'll draw something, that I have a charge that looks like this. The charge distribution is here. And let's assume that this is all positive charge, but it distributes like that. And let's assume that this charge distributes in a weird way. Most of it is here, okay, wherever it's dense. Let's assume here, because charges like like points, they concentrate at points. We will say that we're not going to prove it. It's something that needs more math to prove it theoretically. But let's assume, and then you have charge that goes at the edges like this, at these points, and then it's a little bit less in the beginning, and now at the center. And now this is my charge density here, Q. And now I'm coming to you and tell you that I really want to find how much is the total field that I feel at this point. How are we going to solve this problem? And let's assume that I tell you also that I'm far away, okay? That my R distance here, if this is, let's assume these are distances, all right? The further distances, let's assume that R is very far away from A, B, or C, meaning from this shape, which means that this is going to be much better, much bigger than A, B, and C. Okay, so practically I'm very far away. If A, B, and C are like centimeters, I'm away like 100 meters or 10 meters even. What do you think? How would you solve a problem like that if I were to give it to you and say, you know, find me the solution to this problem? How would you go about doing it?
Professor,
Yes.
if you're far enough away, can you treat the weird shape as a point charge?
Yes, exactly. So what would I do? I say, because of that, and that's what happens with all antennas, because antennas look like this. Some antennas are like reflectors. Some other antennas is like a patch antenna. Another antenna is a dipole antenna. All right. I mean, there are all kinds of antennas out there. But when we are far away and the charge is distributed on these antennas in different ways, we don't see that fine distribution. All right. You don't see what happens here. You don't see how in this weird shape, you know, the charges are distributed. If you're so far away, like it shows here, practically from your point, if your point is P and you're here, and the other, and this weird shape is down there, what you see is a point charge. And this point charge is nothing else but the volume charge, the volume integral of the charge density. So if you can find the total charge Q that is distributed within this arbitrary shape, then practically I can find a center point, my reference point can be at the center. And then from there, if I am very far away from this, like compared to the dimensions of this arbitrary shape, then I can treat it as a point charge. And that's what happens with antennas. We have antennas, of course, antennas, in addition to having the charge distributed in a way that they can radiate, you also have the ability to radiate in specific directions, especially if you have arrays, not radiate in other directions. So you'd send mostly your power, you send it preferentially to some directions. However, the moment I receive from the antenna, to me, an antenna is like a point charge. And the field as along the direction that connects me to the antenna varies like the field of a point charge, which is as 1 over r squared. And that's what you need to remember. And that's what you find from here, from this exercise here, okay? And r here in this particular problem is like the radius, obviously. And we know the direction of the radius is a sub r. And that's why you don't see it here, but I would rather, oops, sorry. I would rather add it here. We don't want to miss it. Please. And put it there, a sub r. Okay. All right. So that is the most important thing that you need to keep in mind. So we found now the field outside of this volume. What happens inside the volume? Now, for me, the good thing here in this problem, if I want to find inside the volume, then the shape of the volume is important, number one. But in this particular case, I have still a spherical symmetry. So when I go inside, I can assume exactly the same symmetry as before. And because of that, I can assume that my electric flux density is a function of radius only and nothing else. No theta, no phi because of the spherical symmetry. So I start again from Gauss's law. And now the difference from the previous case is that my volume is smaller than the volume of the charge. So my volume now, which is this one here, all right, inside that has a surface that is at distance small r from the center of the coordinate system. And therefore, the charge that is enclosed in this volume is this one. So the charge that matters to me is not the charge outside of my volume, but is the charge inside the volume. That is also something you need to remember. When I am inside the charge, the volume, inside the volume where the charge is distributed, what matters in this particular case is the charge inside my volume, inside the volume that I have defined. And therefore, if I follow that, it's this charge that is important and not the charge all over the initial volume. And therefore, inside that volume, the electric field that I feel is due to the charge inside the volume, which is practically, let me see if I can put a little darker color here, this one. All right. So that's the charge that matters anymore if I'm inside. The charge that is outside does not have an effect on me. And you know how you would explain that physically? Because you can say, yes, all of the charges that are outside in the outside volume will eventually, each one of them, apply an electric field, but the total impact, those fields will cancel out. So the fields from the outside charges, they will all cancel out, and the total field that I will feel in my position, and let's assume that my position here is this one. This one, let's assume that I am at that point. Well, on any point of that surface. At that position, I only feel the impact of the inside charge, and it's given by this one. So now, if I am to plot the field, you see that at the center of the volume, at the center of the spherical system, the field is zero. Zero. Everything, the charges all apply something on me, but at the end, it cancels out totally, out of symmetries, obviously. So it starts at zero, it goes to the maximum value, it varies as linearly with R, up until I reach the outer surface of the volume here, at that point. And then it goes down as one. So it goes here as R, here it goes down as 1 over R squared, until I go so far away that practically zero. So any questions about this? Here, for you, I have, as I said, put on a table all of this, and I would like you to do it the same way for yourselves, because this might be more comfortable, convenient, like, or more useful for you to create your own tables. I want you to remember these formulas, to remember how the fields vary, not to memorize the formulas. I don't want anybody to memorize anything. I just want you to physically remember how the fields vary if we have a point charge, if we have a line charge, if we have a surface charge, and then if we have a sphere charge, a volume charge in a sphere. Okay, that's what I want. And as we go and see more complex structures or other structures, I would like you to all classify that in your mind and remember the differences of the fields that come from different sources. Now, before you go, I would like to tell you that I will turn on a, let me see, a top hat question. And since in fact, I was thinking, since, let me see, before you go, because I was supposed to cover something, but I didn't today. Let me see. So I had something on electrostatic potential, but since I were going to keep that as exercise, or maybe I have something in under quizzes. So let me see. Okay, this one. This is also conceptual. It's a quiz, and it gives you charges F1. Excuse me. It gives you a charge F1 and a field, which is F2. Well, no, it gives you two functions, F1 and F2, and it asks you which of these cases is correct. If your charge, first of all, a statement, is it correct that if your charge was to be F1, then your field will look like F2? Or if your charge was to be like F2, would your field look like F1? Or if your charge were to be F1, would your field look like this also? Or if your charge would be like F2, would your field would be like this also? Or none of this is true. So this is conceptual, all right? And it's 1D charge. And you think about what kind of field it can be excited from a charge that is like this. Think on how the field relates to the charge. And remember Gauss's law. You will only be able to solve this problem using Gauss's law. So don't do equations, just think of Gauss's law and what it tells you. This is one-dimensional problem, and Gauss's law tells you practically that the divergence of D equals Q. All right, in one dimension, you have to understand what that means. And then tell me which of the 5 different cases here is a correct statement. And that's going to be your quiz until Monday. So Gauss's law in one dimension. That's all you need to know to solve the problem. Okay, I will assign that as a quiz for week 4. So any questions about that? Any clarifications? You can work with your teams, by the way. You don't need, you can work. Feel free to work with your teams or ask them or have a discussion. That's what I would like to have in these problems. Okay. Yes, go ahead.
We talked yesterday about the team arrangement, and you actually changed me in the office hours. But
Yes.
I'm looking again this morning, and I went back to group 8.
You went? Who took you there?
I don't know.
Okay. I have not touched that, let me go back. Sometimes this system is weird. How many people were in the group? You went back to group A. Let me go back and check it out, because the last time I did it, it was, remind me again the groups. Let me,
I'm now in group 8, and I want to go back to group 9.
okay. I don't know. I have to tell you, I did not touch it after I did it on Wednesday. So, but okay, we'll check it out. Sometimes I don't know what the system is doing. Okay, group 8, group 8 to group 9. Okay, and that's Assam, isn't it? Assam, is that you?
Yes.
Yeah. Do I pronounce your first name well, or is it Assam or Assam?
It is awesome.
How?
Awesome.
Awesome. Okay, perfect. Okay. Thank you. All right, I will go right now and fix it and see. And if you see again change, let me know. I don't know. I mean, once in a while, Canvas has its own problems, unfortunately, but eCampus is going out of the picture on this campus. We are not going to use it again. So, all right. Any other questions? Okay, I will assign this one right now. Let me see. What do I need to do? Close. Assign it. Homework. Okay, and okay, I have to move it up. All right, very good. So I will then see you on Sunday if you come to office hours, otherwise on Monday morning. Okay, have a nice weekend.